When I was approached about giving a talk at the seminar series, the name of the seminar series, which is the Fly High series, made me directly think of a talk I had previously given in a bit of a modified form earlier this year, which I started with High We Fly, wireless witnessing and crowdsourcing for air traffic communication security. So it was kind of obvious that I would choose this topic for this particular series. Let me start by giving, if it works now, it works, yes. Giving a very short introduction. You introduced me now already. So I am at New York University, Abu Dhabi, that you see both on my background and on the picture here. We are at the Center for Cybersecurity, have a set of faculty working in security, and you see a picture of my group here that was taken in pre-pandemic times, but it still looks kind of similar. So what our group basically does is we work on different topics in the broad range of communication security, always very practically oriented topics. And there are three main pillars of our research. The first one is on mobile and cellular network security, where we particularly focus on LTE and 5G networks that have been deployed now. These systems have pretty good security mechanisms in place, often state-of-the-art technology that is implemented in them. So our focus in a certain way focuses on the attack side. So here we are wearing our attacker hats and trying to see which loopholes we can still find in those systems. We try to identify vulnerabilities and have come up with a couple of ways of breaking into existing systems. The second pillar of our research is in the broad range of anonymity and privacy. So here we conduct work on Tor anonymity network and on privacy questions, for example, on managing longitudinal privacy of publicly shared online data. That's the second pillar of our research. And the third one, which I will be focusing on in this talk, is on secure localization and secure aviation. And there are a couple of works where we particularly have been focusing on GPS spoofing detection, as well as on ADSB. I will introduce that system. I don't assume everybody's familiar with that, so I will come to that. But this is the main area of research that I want to be talking about today. Okay, so let's get started. When it comes to aviation and cybersecurity, in terms of the intersections of those areas, just as a broad contextualization, there are in some way traditional cybersecurity questions that also come up in the airlines airport context, like access control, like the security of the IT systems. That's very relevant in practical terms, but I find it less relevant from the research perspective. What is more interesting from the research perspective are actually the security of the aircraft and the air traffic control. So the communication and messages that are being sent between the aircraft, from aircraft to ground stations. So what is happening in this sphere? And this is actually an exciting research area that we've been working on. So when we talk about air traffic control systems, there are in particular two prominent systems that are widely deployed and that are used in the aviation context. In particular, there's a GPS, the global positioning system, that is used for positioning, navigation, and for time synchronization as well, not only in aviation and a lot of other application areas as well, but also in the aviation context. And there's a second system, which is called, there are more, but the second one that we are focusing on is ADSB, the Automatic Dependent Surveillance Broadcast System, that became mandatory in Europe a couple of years ago and has also been mandatory now in the US since last year. It is used to send messages between aircraft and from aircraft to ground stations, and it helps with issues like situational awareness of the aircraft, self-separation, knowing who is flying where, basically. Now, when we look at these two systems and we conceptually look at how they work, then the idea of GPS is conceptually kind of the following. We have a number of satellites that transmit satellite signals from known locations, and depending on the time of flight of those signals from the satellite location to the receiver, we get a number of distances from a receiver location to the satellites. So we can basically set up a couple of equations here that have to be fulfilled and resolve it. And as a result of these equations that reflect the time of flights of signals from the satellites at known locations sent out at known times to the receiver, we can resolve these equations and resolve for 4 unknowns, which are the 3 coordinates in our position system, as well as time as a 4th component. What we have here is a system where one-way communication takes place. So we send signals from the satellites to the receiver only. It's public data, so there's no secret at all in what is contained in those messages. Everybody can receive those messages. And it's also unrestricted use nowadays. What is difficult in making GPS secure is that it's hard to secure the signal arrival time. So the positioning itself inherently relies on the arrival time of signals, and this is something that is very difficult to secure. For example, like cryptography as a general technique for making systems more secure cannot help to protect signal arrival times. It can protect the message content from changes or from modification, but it cannot protect signal arrival times. This is what makes it challenging to secure a system like GPS. On the other hand, when we look at ADS-B, where we have messages exchanged between aircraft or from aircraft to ground stations, then there is in some way mutual information that is exchanged, but it's not a classical two-way communication protocol. We also have a public use setting, similarly as for GPS, and there are a number of companies or organizations like the ones listed here, like Flight Radar, RadarCape, OpenSky, that are collecting all those messages that are being sent and make it available for either commercial purposes or for research purposes. But here, what is actually difficult to secure the ADS-B system is not so much that we wouldn't know how to do it. So messages could be protected better here because it's less about the arrival times, but more about the content in those messages. But we have slow regulatory processes in the aircraft industry in general. So that makes it challenging with the existing system to secure it because it's in place already and it's used and it doesn't have security protection built in. Now, I mentioned it's easy to attack, but what does it mean from the attacker side? So the attacker, the threat that we are facing. So about 15 years ago, what was needed was actually special purpose devices to attack systems like GPS. So GPS existed at this time, ADS-B did not exist yet, but anyways, we could, it was necessary to acquire special purpose devices in order to attack those systems. Over the years, GPS satellite simulators became widely available, mainly for testing purposes, but they could also be misused for attack purposes. And what we have nowadays is that we have general purpose software-defined radios, plus a couple of software packages like the GPS SDR SIM that can be used to actually transmit fake GPS signals, for example, or fake ADS-B signals. So this has become very well affordable for just about $1,000, $1,500 US dollars. In terms of the attackers, what can the attacker do with such an equipment? There are different scenarios of an increasing level of sophistication, what an attacker can do with it. It starts from pure interference, where basically a jamming attack is performed, interference that prevents the reception of signals. But it also continues to pinpoint spoofing attack. What does that mean? What is such a spoofing attack? Well, we have an attacker that is using the equipment that I just showed and is attacking a GPS receiver symbolized by this antenna here. And what happens during the attack is that the receiver believes to be at a different location. So the device is not physically moved, but the device believes to be at a different location or having a different time than where it actually is. That is what's happening during the spoofing attack. This was the example of a simple attack, but there are also coordinated spoofing attacks where the attacker may use multiple transmitting antennas. I mentioned before that there are typically 4, but it can be up to 10 or even more satellite signals that are received at the same time. So an attacker can either use one antenna and transmit an overlay of multiple signals over one antenna only, or a more sophisticated attacker could use multiple antennas and then just transmit a subset of the signals over each of those antennas with the goal to replicate the reality better in this way. And there are different ways of attacker models, how sophisticated the attack can basically be in a coordinated spoofing attack. Now the question comes up, does that actually happen in reality? And here just one slide on that. It was practically demonstrated in a couple of scenarios. For example, in 2013, researchers from the University of Texas in Austin used an multi-million yacht at the sea that they attacked using GPS signals. And what they did is they made the yacht believe that it's actually off track by a couple of degrees, which led to the fact that the crew readjusted the trajectory, and by the readjustment, trying to get back on track, it actually made the yacht go off track. So that's something that has been practically demonstrated. So the equipment that is installed there is subject to those attacks. There are plenty of other examples that we have that have been reported in media over the last couple of years. There's starting with in 2011 the first what I'm aware of incident that was attributed to a GPS spoofing attack, where a drone was actually grounded using GPS spoofing, or at least this is widely believed that this is what has happened there. Then it was followed by a number of other incidents on either airplanes. So there was, for example, 2016 GPS interference around the Kremlin in Moscow, and there were a couple of other instances where ships were actually attacked in 2017 and 2019, in the Black Sea and Chinese ports. It's believed that partially there, the reason for the GPS attacks going on was to mask illegal fishing activities in some areas. So there can be very different reasons for doing that, but it gives you an idea that this is what is actually happening in reality. And just looking up more recent news reports, there are thousands of GNSS jamming and spoofing incidents that have been reported. So GNSS as the super description of GPS. Basically, there are different GPS systems like GLONASS in Europe and GNSS as the general term for those. As conclusion from that, it is generally well feasible to conduct GPS spoofing attack, and what this causes is actually making both locations but also time calculations potentially unreliable. So much about the introduction of the area. I would like to now continue and present two parts of the research work that we are doing. The first part is on countering GPS spoofing attack in civil aviation. And the second part will then focus more on the ADS-B system per se. Although the first part, we will also see that ADS-B will come up there. So there are close relations between those two systems. Okay, let me start with the first part. So countering GPS spoofing in civil aviation. What can we do there? The system is as follows. I mentioned that we have the airplanes that are flying. They are using ADS-B signals, messages that contain GPS locations, but they also contain other information, timestamps, any other data from the aircraft. They transmit it to control centers, and they are using the GPS system for actually determining their own locations. And what we did is we developed a system that allows to detect GPS spoofing attacks that are going on, so possibly when an attacker is transmitting fake GPS signals, and also is able to localize the spoofer up to a certain degree. So not only detecting that the attack is happening, but also trying to pinpoint from where the attacker is actually transmitting the fake signals, such that other follow-up mechanisms can take place to stop the attack, basically. That's the first work that I will talk about. The second one is a system that we call Deep Sim, where we actually use that we designed for UAVs, so for drones that use a separate channel satellite images and comparisons, and I will come to that example as well, how we do that. But let me start with our first system, so Crowd GPSSec, how we can detect and localize GPS spoofing attacks on aircraft in particular. What is the idea? The idea is as follows. We have the aircraft that are flying, and there's a network on the ground that is in place that is collecting the ADS-B messages that are being sent out by those aircraft. Typically 2 messages per second are transmitted. A GPS spoofer would now attack a number of aircraft at the same time, in the sense that it impacts the locations that they determine. And they would report these false location messages as part of their ADS-B messages that are sent to the ground network. And what we are trying to do is we would like to identify first that this spoofing attack is happening. So this would be finding a spoofing incident, and then also trying to figure out where the GPS spoofer is actually located. We do that by making use of public ADS-B reports that we accessed via the Open Sky network that makes them available for research purposes. First part first, regarding the detection. So how can we detect that an ADS-B spoofing attack is happening, or that a GPS spoofing attack is happening? There are two ways. The first one, we could say, okay, when there are alternative localization techniques that are in place, and here in particular, I would like to point out to MLAT, which is multilateration. That's a standard technique which has been in use for many years. So if the locations that are determined by other techniques like MLAT, multilateration, is not the same or not close enough to what is reported in the ADS-B messages, then this is a strong indication of an attack going on. At the same time, a second way of identifying an attack is when the ADS-B locations, so the messages that are reported in the ADS-B signals that are sent out from the aircraft to the ground stations, actually when those locations are the same or very, very close for two aircraft, then this is also a very strong indication that an attack is happening, because two aircraft cannot be at exactly the same position at the same time. There would be a collision. They need to respect a certain minimum distance. And that's a second way to basically detect that. And that is what would be typically happening during an attack. When the same attack signals are received at two aircraft, they would report the same wrong location. Now, coming to the second part, to the spoofer localization, the question is how we can make use of this to identify that an attack is happening. And the idea that I will explain on the next couple of slides in more detail, but the core idea is as follows, that the two aircraft will receive those send out messages at slightly different points in time. So the closer the aircraft is to the spoofer, the earlier the fake signals will arrive. The further away the second aircraft is here, the longer it will take. And as a result of that, also they will calculate the same wrong location, or actually the same wrong trajectory, because the attacker for an aircraft will obviously try to spoof a trajectory and not an immobile location. But the effect of this is that the aircraft that received the attacker's messages earlier will appear earlier on the spoof track than the second aircraft that looks like falling behind. And based on this idea, I will show you in the next couple of slides how we actually use this to determine the location, or to derive information about the attacker location. And we then, we implemented the systems and used our simulations to actually get an idea about how the performance such a system would be in reality. Now, let me focus on the central block here, on the spoofer localization part, which is the most interesting part of that. And here, let me very shortly introduce the idea of aircraft multilateration. So that is the standard technique that has been used for many years in the past. And the idea is as follows. It's fairly simple. When we have two locations, two infrastructure locations, like these two sensors, S1 and S2 on the ground, and there's a certain distance between the sensors and the aircraft, then obviously the signal arrival, so the signal travel time from the aircraft to the sensors will in some way correspond to the distance that is traveled. So obviously the signals will arrive earlier the closer the sensor is to the aircraft. And by using the signal arrival time of the same signal that is sent out from the aircraft and is received at two different receiver locations, we can calculate an equation that has to be fulfilled of possible locations where the aircraft can be. And the only thing that matters here is the difference between those two distances. So the difference of the time of flight from the aircraft to sensor 1 or to sensor 2. In 2D, this would be reflected by actually the aircraft being limited to being somewhere on a hyperbole here. In 3 dimensions, it would be limited to a hyperboloid of where the aircraft could be located. Now, multilateration doesn't work with only 2 sensors, because then we still wouldn't know where on this hyperbole the aircraft would be. That's why more sensor locations are taken into account. And when we do the same thing, we can set up the same equations again, and we will get a couple of more hyperboles that are defined by the new sensor pairs. If we do that well enough, then those hyperboles here will intersect in one point or be close to one point. Of course, there are errors in reality, but this will be close enough to one point, which gives us the location of the aircraft. Now, we use the same idea of multilateration, but turn the problem around, because we want to identify the location of the spoofer. But the idea is similar. We take the distances from the spoofer to the aircraft into account. These are the flight times here that are relative to the distances traveled. And as I mentioned, the earlier the signals are received, the further ahead on the spoof track the aircraft will appear during a spoofing attack. And this distance between where the 2 aircraft will actually be located on the spoof track gives us a way to now find a hyperbole of where possible attacker locations can be. So we turned basically the problem around, have 2 aircraft here now, and this time difference of arrival now determines possible location of the spoofer. Again, we don't have to stop with 2 aircraft here, assuming that there are 3 aircraft in the same area and sky that receive those spoofing signals. Then we can do the same technique as for multilateration, can use more hyperboles or hyperboloids, and the intersection resolving those equations will result in something that's kind of close to the attacker location. That is the core idea. There's one little thing that I would like to hint on, which is in our equation here, we have V here as a denominator, which is the speed of the spoofed aircraft track. So how fast the aircraft appears to be, or is trying to be by the attacker, what the attacker is trying to spoof. And obviously we see this cannot be 0. So this system will not work for stationary devices, because then we would get a 0 in the denominator here when the whole system would break. So we need actually devices that are traveling, and we need the speed component. That's why we proposed it for aircraft. Now, putting all that, we've made systems with simulations. We feed it with real-world data. We get certain dependence on the track velocity. So the faster the spoof track is, the better the system will work. We see here the distance to the spoofer. So that's basically symbolizes the accuracy of our method. The faster the spoofed aircraft track is, the faster we are able, and the closer we will get to the real location of the attacker by this way. It will not always work. If our speeds are too low with, for example, 5-6 kilometers per hour, then this whole system will break. It will not work well. We need kind of high speeds for that. But this is the core idea. We can compare it to MLAT. We see that there are certain differences and certain similarities in the way how the systems are. But if I just want to summarize it here, what we have developed is a technique that through indirect measurements from ADS-B position broadcasts that contain GPS calculated positions, we're able to localize GPS spoofers up to a certain degree, up to a certain level. So we are able to pinpoint the attacker locations and limit the locations where the attacker can be positioned. And this is, as far as we know, the first proposal of a GPS spoofing countermeasure that takes advantage of the indirect GPS signals that are contained in those ADS-B messages instead of working directly on the raw GPS signals. It works also pretty well without a line of sight between the ADS-B receivers and the spoofer. So the ADS-B receivers and the spoofer, there doesn't need to be a line of sight connection between them. And we don't need any particular further extra infrastructure. So it only relies on the data that are being collected anywhere already now. This was basically the first idea that I wanted to present. I would like to shortly and with a little bit less detail go also into the second proposal. In particular, I mentioned this requires kind of high speeds. With UAVs that are sometimes hovering and are going slower, this is something that will not be possible to apply it to in this context because the speeds are not high enough. So what we did here is we actually used another separate channel. In particular, the camera that is installed on many or most of the UAVs that are deployed nowadays and that are being used. And the idea here is that we use the visual images taken by the camera as a second channel for verifying the location that is determined by GPS and for possibly correcting that as well. And the idea here is as follows. So we would take, we have our UAV that is getting GNSS data, GPS data, that claims the UAV to be at a certain location. It can take aerial photos of that and can take a picture of the ground, how it looks like. And we can then compare it to satellite images as we would expect them at that location, depending on the calculated GPS location. So basically what we do is we take images and we compare them to what the UAV would expect to have, would expect to see on ground. What we see here are just a couple of examples for that. Below here, you find satellite images as taken from Google Earth. And on the top row here, you see images that we collected in China as well as in Switzerland. And you see that there is quite some resemblance of these pictures. Of course, there are a number of challenges that I left out here, which is when you take those pictures, they will be of a different resolution, they will be in a different direction. There are less real weather conditions. There's a lot of things that matter and that need to be taken care of, but that's the core essence. We would like to see if we can actually match those images from the pictures being taken and the satellite images that are publicly available. Now, what we do is we feed both of these satellite images and a large set of training data from aerial photos into a deep learning, machine learning model, and have then two ways, either executing that on board, on the air, on the drones, on the UAVs, or on ground, where the UAV would just transmit the photos, and then the verification checks or the spoofing indicator is determined on ground then by running these machine learning techniques. That's kind of the second idea of how we can detect GPS spoofing attacks on drones. We ran that through a number of simulations again, or we used prototype implementations on Raspberry Pi like devices that represent the capabilities of what drones would have on board. And we found that we achieved pretty surprisingly good accuracy for the technique, actually. So we were able to detect pretty well when spoofing attacks are happening, so other locations are reported, or when the correct location is being reported. There are a number of things we can think about when this technique will work. Obviously, it will work much better in feature-rich landscapes. So on top of urban areas, for example, it will work much better than when you look at like deserts or forests, maybe even. We've taken into account data augmentation in the sense that images may be cloudy or bright or dark and blurry, and we've used a whole big set of data to input into our systems. And I mentioned the experimental results on Raspberry Pi-like hardware. In general, this would be applicable to commercial airliners as well, because they do have cameras as well. But obviously, this will not work well above clouds. So that's why it's maybe not the best application area for commercial airliners, as well as over the sea and on deserts, because there we are missing the features from the landscape to actually do this matching operation. So this was the second idea that I wanted to pitch regarding the GPS spoofing detection. And what I would like to do now in the third part, the last part of the talk, is to go a little bit more into detail on ADS-B spoofing. So far our focus was on GPS spoofing attacks, so attacking the GPS system. And we also thought about what we can actually do to identify ADS-B spoofing attacks. So the message is sent between aircraft and from aircraft to ground stations. In particular, the way how this looks like is so the aircraft are transmitting their identifiers, the ICAO, the data, so that's position data, speed data, and a lot of other data. And an attacker may record this data and resubmit it later on, or an attacker may also insert it, new fake bogus data that was made up by the attacker, transmitted either from ground or from another airplane. So there are very different possibilities. And also the system may be attacked on the receiver side here, in particular for systems where the collecting infrastructure is not trusted. So there's, for example, for OpenSky, in that example, it's a voluntary network where people collect to put up receivers, and there's no way to basically trust them. It would be easy for an attacker to insert bogus data also on the collecting ground station in a certain way. So we model that by, I'm coming to the attack, but our question for this research work was basically, how trustworthy are those received ADSB messages? How can we distinguish legitimate from fake ADSB messages? The attackers that we consider include GPS spoofers, as I mentioned before, where the attacker tries to steer away the calculated locations of an aircraft from a certain track. But it also includes direct ADS spoofing attacks, where one or multiple or all of number of receivers are being attacked by the attacker. So the attacker would insert own made up data basically, and insert that as signals being sent out and received by the infrastructure. And we also consider the sensor control, so this last part of the attacker, where the attacker would directly take control over the sensors and introduce fake data there. Just to give you an example, the OpenSky network, I mentioned that before, we are displaying 1 day of data. We collected 1 day of data for this representation here. And what you see is the map of Europe and the number of messages that are received at all of the different locations where ADSB sensors are receiving messages. So where they are deployed and where they are receiving messages. And there are hundreds, thousands, 10,000s of messages that are being received depending on the location. What is very important here is that, so we used, it's one day of data here, a typical pre-pandemic day that we used here. We used data from February 15, 2020. What you see here is basically that at many locations, there will be at least 10 sensors or more than a handful of sensors that will receive the same ADSB messages. And this is exactly what we leverage. We leverage this redundancy. So there is redundancy by the messages that are received at different locations. And we use that redundancy in our proposal to detect attacks. And this is what I want to show you on the next slides. The core concept is that we use spatial redundancy of the surveillance network, and we do that in a collaborative manner. So all the sensors are feeding in their data, and we are able to evaluate that in the end. We are collecting, using those crowdsourced messages, ADSB messages, and we basically process them as discrete sensor events. Was a message received or was it not received? And try to detect inconsistencies by that. In a certain way, it's a very simple approach where we don't make use of measurements, additional measurements of time or of Doppler shift or any other physical mechanisms to identify attacks, but we really base it only on the received, so which sensors received which aircraft messages. We use machine learning approach here as well with a decision tree based approach, and try to identify what is the attack that has happened if an attack is being detected. Was it GPS spoofing? Was it ADSB spoofing? Was it sensor control? And so on. The core idea, just visually, what is the core idea of that? The core idea is something that we call wireless witnessing, which we can describe as a collaborative process of observing the status of a distributed wireless system, which is something that we have here. And the question is an observed ADSB message with a claimed aircraft ID, is it real or not? And you can look at the example like this. If there are only 2 sensors that did not receive a message, then this is what happens in wireless systems. Messages can get lost, they are not received, there might have been an obstacle on the way, whatever. If it's only a few sensors that did not receive it, then probably yes, it's a real aircraft if all the other sensors received this message from the aircraft as expected. However, if the majority or a lot of sensors did not receive it, but only a few sensors actually report this message, then it's very likely that an attack is happening, that these, for example, these sensors here are trying to insert fake data into the system. And that is what we use. We basically consider whether reports are received or are not received, first under normal operation for training purposes. We simulate attacks, we simulate GPS spoofing, ADS spoofing, and sensor control. from that derive labeled reception patterns on our data set that we use from the Open Sky network, and then run a machine learning based classification where we use decision trees as an approach. The entire process is so the system itself is more than just these wireless witnessing that I mentioned now. There are a number of other checks that we can do, sanity checks, differential checks. So aircraft can only be at certain height levels. They can also only have certain speeds. We can do all those checks. But then the important part is this sensor coverage here, this cross check. And this is basically the core of the system based on the idea that I presented on the slide before. Now we run all those checks. If some of them fail, then we try to run an attack analysis, try to figure out what type of attack is happening, what are the affected sensors, and if not, everything is good. We have kind of more trust and more belief in the data being correct. I will not go into too much detail here. I'm aware of the time, but just to give a few ideas here about the performance that we achieved with the system. So when we focus on GPS spoofing, and here we have certain deviations from the expected track by degrees, so by 1 to 5, 10 degrees, we deviate from the expected aircraft track. We consider detection windows in terms of minutes. We don't take decisions based on individual measurements, but only on a window-based approach where we take a number of measurements into account, and then are able to detect the attack with kind of good accuracy and with some detection delay. So because we have this sliding window approach, there will be a detection delay that we use. But by that approach, we are actually by design able to have a 0% false positive rate, meaning that so this whole thing is threshold based, and we base it on the observed data for this particular day here. So this is designed in a way that we don't get these false positives. So we don't get false alarm on the system, because this would be very disturbing. And that's just a matter of design here, how we get it. If it's deployed in reality, we might have to adjust these thresholds and may then see some false positive rates here, but that's the way how we evaluated our system. So it's optimized towards these 0% false alarms with respect to this one day of data that we used. In terms of time, so after a couple of minutes, depending on how much deviation there is, so how fake the data is that it's being introduced, how much the airport track deviates from the legitimate trajectory. After a couple of minutes, we can pretty reliably identify that the attack is going on. So it typically just takes a couple of minutes, and obviously this depends on how false the data is in a certain way. So the larger the deviation is, the faster we are able to detect it. So much about the GPS spoofing. With ADS spoofing, that's similar. As soon as an ADS-B spoofer that inserts wrong data into the system, as soon as that happens, then it will impact. So we notice it pretty directly that the attack is happening, no matter if it's only a single or multiple or a whole set of sensors that are being attacked. With reasonable detection rates, we are able to detect it pretty quickly that the attack is happening, because we don't have this large sliding window approach here. That's why we are able to detect it faster. I don't want to present much more data, but just what in the way how we designed it, we received a 100% correct classification for the normal aberrations. And there are some misclassifications between, for example, when we expected GPS spoofing and it was ADS-B spoofing going on, and vice versa. But these are parameters that will have to be varied anyways when this is deployed in the real world. Our observations or lessons learned here is that we were actually surprised that already with a kind of simple decision tree based machine learning approach that described the data, it was actually a plausible model for our data, and we could, with this pretty simple machine learning approach, already get kind of good results out of that here. The challenge was certainly working on a large set of messages. So one day of data is more than 200 gigabytes of data. If you try to process that and use that in learning, I mean, there are quite some overheads with that were actually challenges in that here. Source code is available, yeah, that's what we all share about our approach. That brings me to the summary and conclusion, takeaway messages here. I've presented you a couple of proposals, Crowd GPSSec, DeepSim, Trust the Crowd, where we use different approaches for detecting GPS spoofing and ADS spoofing attacks. They are applicable in different contexts. Some require moving targets, like the first Crowd GPSSec idea, where we need moving aircraft. Others might need cameras. So there are separate channels that we need. And there's also a different level of required integration into the air traffic control infrastructure. For some of them, they need to be integrated into the ground infrastructure. For them, they can be on drones or on aircraft directly. So there are different techniques to actually to identify that attacks are happening. There are still open questions, obviously. How does, for example, on the first one, how does GPS spoofing in reality affect the positioning and navigation in civil aircraft? There's no public data available for that. And obviously, we can't just attack aircraft flying around. So this is something we cannot do. So there's there are some open questions in this area, as well as for the last example that I showed, how much real world overhead is there for trusted route? How well can we adjust the thresholds, and what will then be false warnings and misses in the real world? So this is still open. It brings me to my last slide. In the way how we've considered it now, it doesn't seem to be the case that there would be a one-size-fits-all solution for cyber attack prevention in civil aviation, but there are a number of approaches that our group and other groups have come up with. It is important when we look at the number of attacks that are happening and that are increasingly happening. I showed examples for GPS spoofing before, that these are integrated into the cyber defense infrastructure as protection and prevention methods. So that's something that is important. I'm pretty much at the end of my talk. If you are working on related topics or have questions, I'll be very happy if you either speak up now or get in touch with me at a later point in time. My email address is here. Thank you very much for listening.